Hello and welcome. In this tutorial we will code a gorgeous, elegant and powerful prime number generator in ImageJ. We will export the code to C++, we will identify and avoid pitfalls, and we will optimize the code up to, no bullshit, 19 million primes per second. What do you need? At first, ImageJ, I personally recommend Fiji. You need a C++ compiler like Dev C++ or Visual Studio, and you need Microsoft Excel or at least something similar. First, a few words about ImageJ or Fiji and why I just love the software. There are hundreds of programming languages like JavaScript, C, Python, Visual Basic, Delphi, Pascal, Go, Julia and so on. Each one better than the other, each one more or less perfect to start with. But almost no review mentions ImageJ or Fiji. ImageJ or Fiji is a free image editing software. It has a very powerful script editor that uses a very simple version of JavaScript called ImageJ1 macro, and consequently Fiji is so much more than just image processing or editing. It is a massively underestimated programming platform. If you use ImageJ1 macro, you have a quick familiarization and quick success. You have code that can be almost easily read by humans. You do not have to include libraries, you can start right away, and you have autocompletion. If you start typing, autocompletion kicks in. Furthermore, every single command is explained exactly and linked to examples. You have just a few commands and a massive fun factor. Fiji is a version of ImageJ that already contains countless plugins that focusing on scientific image processing. Both are available for free and you get regular updates and patches. The software doesn't have to be installed, it's portable and so you can use it on computers even without any administrator rights. Here you can find a complete list of every single command with a detailed description of it. This language is like Lego, you can form complex structures from very simple blocks. In our concrete example, as mentioned, we built a prime number generator in ImageJ and also in C++. Don't panic, it won't be the boring dull brute force calculator. Our one will be beautiful, elegant, and it calculates shockingly little. And you can download all the codes presented and discussed here. First, what is a prime number? Prime number or prime is a natural number greater than 1 that is not a product of smaller natural numbers and therefore only divisible by itself and by 1. 1 is not a prime number. All non-primes can be created using prime numbers, but no prime number can be created that way. Primes just can't be arranged as products of other numbers. Every number n that is not a prime can be written as a product of prime numbers that are smaller than n, or to be precise, smaller than the square root of n. This process is called factorization. The non-primes 15, 25 or 143 can be written as products of prime numbers. And the smallest of these prime factors is smaller or equal to the square root of those numbers. So if you want to know if 101 is a prime number, just square root it. The root is roughly 10, so you have to test 2, 3, 5 and 7. The 11 is already too big. And because 101 can't be divided by 2, 3, 5 and 7, it is a prime number. It has to be. But that's easy. If you have something like 50,485,863. There are already 546 primes that are smaller than the square root of this number. And because this number is prime, you have to actually calculate all 546 of these single tests. However, with our generator we want to reach 10 plus billions. And so we would have to run almost 9,600 tests for every single number in this range. We see brute force testing is not an option and so we will avoid testing here at all. If you arrange numbers like this, you will quickly see that all prime numbers are either multiples of 6, minus 1 or multiples of 6 plus 1. So we just have to look at two columns that are here called array A and array B. Not all of these numbers are primes, but all primes starting from 5 are found exclusively here. Looking at all the other arrays is just waste of time and memory. An array is just a list of elements. Here those elements are prime candidates and we call our arrays A and B. In Fiji the according code looks like this. We create array A with 1 million elements and we create array B just as copy of array A. And then we fill those arrays with prime elements using a loop. The array name .length returns the length of the according array. And our single elements are numbered starting at 0. This is important. They do not start at 1, they start at 0. Now we have two arrays A and B with prime candidates. Cool! But how to get rid of all that boring non-primes? We start with the first element of array A. We read its value, here it is 5, and we start deleting from element 0 all the following elements using 5 as increment. So we delete element A5, 10, 15, 20 and so on. All these elements are multiples of 5 and here delete means in fact replace with a 0. There are two reasons for this. Actually, deleting an element means that all the following items must move one place to the left. If you do this once or twice, it may take microseconds and you will not even notice it. But if you loop microseconds for 100 millions of times, your program will become painfully slow. The second reason is we need the exact position of those elements later, so we can't just push them around. So if I say delete, that actually means in the code that we are overwriting the non-prime number with a 0. Those zeros will be removed later with a single command very quickly without any loop and shifting of elements. Where are we now? Look at the blue lines. You can see we just deleted all the multiples of 5. Now we take the second element of the array, A1. We read it out, that's the 11, and now we remove, starting from A1, every 11th element. A12, A23, A34, A45 and so on until we reach the end of the whole array. Look at the red lines, all those elements are multiples of 11. And this is exactly how we continue with every single element that had not yet been replaced by 0 and is bigger than 0. We do not have to calculate, we do not have to factorize numbers, we just have to count and delete. It doesn't matter if the number to be deleted has 2 or 200 digits. In arrays this happens lightning fast. Larger numbers do not cost us more time. Only the amount of elements to delete determines the duration of this process. Array A is completely self-cleaning. At the end of this process there are only prime numbers left in array A. However, with gaps, because there are of course lots of primes in array B that are still missing for the complete list. To code such a process we need rules. The rules here look like this. Element 0 starts deleting from element 5. Element 1 deletes from element 12, element 2 from element 19. So deletion starts at element 7x plus 5. The increment of the deletion is the value of ax, and if we find an element that has already been zeroed, we skip on to the next, to the next, to the next, until we find an element that is bigger than 0. Now we clean array B. That's a little bit more complicated, but we start exactly as we did with array A. We take the first element B0, in this case a 7, we delete its multiples starting from element B7, in this case the 49. Then we delete the multiples of element B1, that's the 13, starting from element B14, in this case the 91, and so on until the end of array B is reached. But Here the delete from element formula is not 7x plus 5 as in array A. Here in array B it is 7x plus 7. Unfortunately, as mentioned, array B is not completely self-cleaning. The squares of the prime numbers of array A are found only in array B. So we need array A in order to be able to delete several non-prime numbers from array B. Of course, the squares of prime numbers are never prime numbers themselves. Now, deleting the squares of the prime numbers of array A from array B. And we have furthermore to delete the multiples of those primes from array A, starting from its square in array B. So, figuring out the rules. Element A0 has a value of 5. It starts deleting from element B3 that has a value of 25. Element A1, the 11, starts deleting from element B19, the 121, the square of 11. And so on. The formula that brings you from the element in array A to its square in array B is 6x to the square plus 10x plus 3. Starting from there, the elements in array B are deleted using increments of ax. So element A0 is the 5. It starts deleting from B3 in increments of 5. Element A1 is the 11. It starts deleting from B19 in increments of 11 and so on. But most of us are not Ramanujan. They are not coming up with such a formula just by looking at some numbers. So where does this formula come from? To solve this we use Excel. We just pair the A and B elements, we plot the curve and we add a trend line. We select polynomic and show formula in diagram. And there you are. That's perfect to play around quickly and to test ideas. This formula will not be our last problem of this kind. And there are many programs that can fit curves like this. And we are done. In both arrays A and B, all non-primes are already replaced by 0. How does the according code for ImageJ looks like? Back to array A, we want to clean array A of non-primes and delete the multiples of every single element in array A. So we start with two nested loops. The first loop starts from array 0 and goes to the end of the whole array. If the element is already zeroed, we skip on to the next one until we find an element that is bigger than 0. And now the deletion loop starts. It starts deleting from 7i plus 5 and it uses the value of the element ai as increment and it moves on until the end of array A is reached. 3 lines of code that zero all the non-primes of array A. At the upper half of the slide we see what we just did to array A. Now we apply the same to array B. We use two nested loops. The only difference is that deletion starts from 7i plus 7. And now we have to zero the squares of the primes from array A and also their multiples in array B. We start in array A and we zero the according element in array B using the formula we know that brings us to the square of it. And then we go on using ai as increment. If ai is already zeroed, then it was not a prime and we directly skip to the next element until we find a prime. And then we start a loop that deletes on. It starts from the square of the element found in array A and it uses the according element ai as increment, deleting elements in array B. Now we are almost done. We have two arrays A and B that contain only primes and zeros. All that's missing is some cosmetics. We delete all the zeros from the arrays A and B in a single step using a single command without looping. We insert the missing primes 2 2 and 3. We merge both arrays. Here array A becomes array A plus array B, and then we sort our results. And